Judging by the looks of the homework, we might have a few to go over here. And that's okay. That's kind of to be expected here on this section. Now, a lot of people in this morning, and that's good. Let's go through a couple of these things, and we're going to go through this in some depth because these are the problems we need to be able to do. Let's focus on differential equations here for the first part. This is what we need. This is the new thing. All right. Now, this line right here is you've just got to repeat this over and over to yourself, right? I mean, just really have to have this cold. The solution to a differential equation is the original function y. These are the notes from yesterday. They're up on the website. Okay, if you want to get them, but the solution to a differential equation is the original function y equals f equals h equals p equals whatever, with no primes on it and only x's or t's or whatever the input variable is on the other side. Okay, the solution to a differential equation is the original function y. A differential equation is any equation that contains one or more derivatives. It means y primes, f double primes, y double primes, h primes, p primes, whatever. Any equation that's got that in it is a differential equation. Now, let's look at number 20. Number 20 said, what did it say? T, something like that? Okay, what did the directions say exactly for number 20? Alex, Marbles, read it to me. Are you on that page? Who's on that page? Spencer, read me the directions exactly.
An exercise 19 through 22, decide whether the function given is a solution or the differential equation.
Okay. Decide whether the solution given is a the function given is a solution to the differential equation. Is that what it says? Which one of these is the solution and which one of these is the differential equation? This is the solution, right? That goes back to the previous thing I was just showing you. The solution to a differential equation is the original function y equals. Now, the y of t, to be honest, usually we don't even write that in there. And I'll be honest, I'd rather write this as 1/2 t squared. I think it's easier to work with. But I would usually rewrite it this way. The t in there just kind of, gets in the way. I don't think it's really necessary there. All right? This is the solution. We want to decide if it is a solution of this differential equation. That is like if I gave you x squared plus 4x equals 2 minus x cubed, and I said, is x equals 3 a solution? If I gave you this problem and asked you if x equals 3 is a solution, Dakota, what would you do? And then what? Plug in a 3 for x and then what? Work each side and see if the two sides are equal. Now this is why I said do the t-chart. Now you probably wouldn't have thought of doing a t-chart, right? You would just plug a 3 in here, keep those in your head and see if they were equal. And then if they weren't, you'd say not a solution. And your reason would be because they're not equal, right? Now a lot of times I'll get people who answer that by saying, well, I'll plug a 3 in and see if it works. Well, that's pretty generic. I mean, what do you mean works? Well, what he said, right? What works means that when you plug it in, that this side is the same as this side. That's what it means in this case to work, right? But we're so good at these and we've got so much experience with these that we can use generalities like that and get away with it. But now we're into this new thing that we don't understand as well and we haven't seen as much, and so now it gets confusing. So that's why I give you the t-chart. Somebody in the other class, Josh Lilly, he said, well, I just thought of it this way. He said, I just thought, well, y is equal to this, and y prime is equal to, and then he did the derivative, right? Bring down the 2, and you get what? T. And he said, I just looked and y doesn't equal y prime. So I just, so would it be, his question was, would it be okay to just say, no, this is not a solution because y, which is this, does not equal y prime, which is this. And I said, that'd be fine. For that one, that'd be fine. But for other ones, I don't know that that would be as easy to explain, right? But his process and his thinking was great. That's fine, okay? So I give you the T-chart saying you don't have to do the T-chart, but the T-chart is just a way to organize your thinking and show it and justify it in a way you don't have to write any sentences, and it works all the time. So that's why I give you the T-chart, okay? But I liked his thinking in that he was understanding what was being asked. Okay, so the T-chart way of doing it would be, okay, I'll substitute a y over here. This is like what Dakota said. Dakota said, I'm going to take my solution, I'm going to plug it in, and see if the two sides are equal. So I'm going to take the y and put it over here. I'm going to take the y prime and put it over here. Are they equal? No. So it's not a solution. That's it. Okay? Let's do another one of those verify ones, because that is definitely going to be on the next quiz. We have to verify a solution. Maybe multiple times. Got another one you want to do? 25, 6, 20, 25. Okay, what did 25 say? Miranda, go.
Y equals x squared.
Okay.
Is y equals x squared a solution of
Differential
the
equation.
equation
Yep.
of y double prime minus 4xy prime plus 4y?
So is this a solution of that? So, right? I put the T-chart right there, and I want to plug this into here. Well, I can plug this in for that y, but I need a y prime and a y double prime. So over here, I'll just work out y prime is 2x. Y double prime is 2, right? So now I'm going to plug those in. So y double prime is 2, 4x, and then y prime I'll plug 2x. And for y I'll plug x squared. And of course there's nothing over here, that's just 0. So this is 2 minus 8x squared plus 4x squared. I mean, as I'm going around looking at your homework, I'm not seeing this level of work written out. So I'm guessing, as I'm looking at things, I'm seeing a lot of people with problem written out and maybe not much else written, right? It's first day, so I get that. But had a good crowd in here this morning. I wondered if maybe you could have been bigger. But anyway, no. Not the same. This side is not the same as that side. Didn't work. So y equals x squared is not a solution. I think I should make one comment about 6. We did talk about this morning, so those people have seen it. But they asked if this was a solution to, what was it, y prime equals 1 over, no, negative 1. Now, some of you may have not had a question on 6 because you copied the problem down wrong, and it wasn't your fault. The book, I don't like the way the book wrote that. If you thought it said 1/2 y, it did. It was supposed to be this. Okay? So if you did that, that would change, well, a little bit. It would change, it would change it quite a bit as far as the ending. But the key part of the problem, actually, the key part of the problem I want to do is talk about when you do the derivative. So we're asking if this is the solution here. So my T-chart will be here. And I'm going to see if this will plug in and make these two sides equal. Well, so I need to do y prime here. Right? Now remember, c minus x is the same as c minus x to the 1/2, right? C minus x squared root. So when I do this derivative, I bring the 1/2 down in front, leave the inside alone, drop that to negative 1/2, and you guys that were here this morning, we got to kick out a negative 1. Why? When you multiply, okay, let's think back to sine 2x. When you do the derivative, you got to kick out the 2, right? Because the 2 is times the x. Well, right here, you got negative 1 times the x. So you gotta kick out that negative one. Okay? Any number multiplied by the x inside the function has to get kicked out because that causes that compression or stretch. In this case, it's a flip, actually. But that's going to affect the slopes. If you flip something this way, it's going to affect the slopes. They're going to be opposite. Instead of going up, they're going down. All right, so now, y prime, and I'm kind of running into myself here, y prime then would be negative 1/2 c minus x to the negative 1/2. On this side, I'd have negative 1, 2, and then I'd have my y is c minus x to the 1/2. That goes in for y. Now those two, you can see they kind of are the same. If I just flip this negative power down to the bottom, those two are the same. So it checks. All right, and then they ask, what about this solution? Would this be a solution also? Turns out it would be. Think about what would happen. If you bring the y prime down in front and kick out the negative again, the negative will cancel the negative and the y prime will turn positive. So this side will be the same, but it'll be positive. Well, on this side, since your y is now negative, when you substitute it in for the y, you'll have a negative down here that will cancel that negative and it'll be positive. So both sides will turn out positive, so they'll still be equal. So it turns out this is a solution as well. But you would have to work that out. But okay? So we'll get to practice some more of these verify ones for tomorrow or for Monday. But verifying that something is a solution. So if we go back to the notes from last time, we said that was one of our differential equations, number 2 down here. You know, a differential equation that we don't know how to solve. It's got y's in it, x's in it, y primes, that kind of thing. We don't know how to solve that, so we have to be given the solution, and then we can verify it's a solution, and we showed how to do that. Then we've also got these kind of simpler ones with just x's in them, or little t, if t was our input variable, where we can just do the antiderivative to get the original function. And then we talked about this one, this bank interest one, and we'll do an example of one of those right now. We'll talk about that money one, the bank one. Matter of fact, this is just like that. This is just like number 20, as a matter of fact. Right? We had y prime equals y, so it'd be k would be 1. So the solution to that would actually be that right there, ae to the kt. Kind of makes sense, actually. What do we say about the e to the x function? It's its own derivative. So y equals y prime. Right? So it makes sense. But now, it's not just e to the x. What if y was 3 e to the x? What's y prime? 3 e to the x, right? So you could have a number out in front of e to the x, right? So the solution to this differential equation is y equals ae to the x. And if you look at our notes, if k is a 1, y prime equals y, put a 1 in for k, we get ae to the t, the same as ae to the x, right? So that kind of makes sense, all right? But that's exponential growth. Any exponential growth problem like bank interest, stuff like that, is going to fit that model. Okay, let's look at, was it 47, 48? Well, 43, yes, I want to do 43 also. But what was the one with the 47? Now, I gave you that equation, right? It was, the problem said p prime equals 0.08 p, right? Well, that's the same as y prime equals ky, right? And the solution to y prime equals ky is y equals ae to the kt. So this should be p equals ae to the 0.08 t, right? So what do they tell you? Put $2,000 in the bank? Okay, so at this point it's a basic advanced math problem. It isn't even that hard a problem. What that means is at time 0, you put in $2,000, right? So at time 0. Well, what happens? If you put in a 0 there, you get e to the 0, e to the 0 is 1. You get A is 2,000. So that's why we always think of the A as the beginning amount. So my equation is 2,000 e to the 0.08 t. And now they say what, 2 years later? 10 years later? You put a 10 in for t, work that on your calculator, and there you go. Okay, so if we have a problem like that, it should be pretty easy, right? Especially if I can give you the equation. Okay? All right, let's talk about 43. Because this is something else I want you to be able to do. This is everybody on page 130. Everybody look at page 130, and if you haven't, well, hopefully you at least read it for the homework, but if you haven't, and if you did, let's reread it. Page 130, number 43. Okay? The rate at which the temperature of an object changes is proportional to the difference between the temperature big T of the object and the temperature S of the object's surroundings. Express this law as a difference equation. One of the things I said to you yesterday is the importance of difference equations is they can model realistic physical situations quite nicely. The downside of differential equations is they're not very useful in finding values that we would find important. So after you take calculus in engineering, you take a course in differential equations, being able to solve differential equations, because by solving the differential equation, you find the original function, which can find you those values you need. So I want you to be able to take that language and be able to write a differential equation. So let's break it apart and let's think about it. They tell you big T is the temperature. Let's say we had a hot cup of coffee sitting here. So big T would be the temperature of the coffee. And S would be the room temperature. Okay, the surrounding. All right, it says the rate of change of big T. Now how would I write that? The rate of change of big T. Isn't that it? I mean, rate of change should make you think of derivative. We're writing a differential equation, so it should have a derivative, right? So big T prime is proportional to, okay, let's think about that a second. If I say to you, this is something we all need to know. If I say to you, y is proportional to x, what I'm telling you is y equals k times x. That's what that means. If y is proportional to x, then y equals k times x. Because if numbers are proportional, like 2 to 6, 3 to 9, 4 to 12, those would be proportional. What would be the equation that would represent those numbers right there? What would be the equation that would represent those numbers? Y equals 3x, right? 3 is the constant of proportionality for these numbers. That's what the k is. So when you read y is proportional to x, stick a k in there. So when they tell me that t prime, the rate that t changes, is proportional to, I put an equals and a k like that. You're going to have to be able to do that. Okay? Very easy. Now, inversely proportional would mean y equals k over x. So we'll talk about that situation in a minute. Okay? But proportional or directly proportional to is that. So, now what is it proportional to? It's proportional to the difference between the temperature and the surroundings. The difference between T and S. So how would I write that? There you go. That's all you had to do on number 43. That's all you had to do. Is put that into language, and that's a differential equation. Yes? The K, okay, back to this one. The K is the constant of proportionality. How are they proportional? These numbers are proportional by a factor of 3. Okay? So it's whatever that constant of proportionality is. Now for coffee, it might be 1K value. For some liquid in the chemistry room that was cooling, might be some other constant, right? It would depend on the chemical properties of the liquid, probably. It could depend on the insulating properties of the cup it was in. If I've got coffee in a ceramic mug compared to coffee in a styrofoam cup, styrofoam cup's going to cool at a different rate than this will, right? So the K would be different, all right? So it would depend on those factors. That's what the K would be. All right, now let's think about this a minute. When two things are proportional, it means as this one gets bigger, what happens to this one? Gets bigger too. Again, by how much? Well, by that K factor. Now, an inversely proportional works the other way. As X gets bigger, what happens to Y? It gets smaller because that's in the bottom. So as one gets bigger, the other gets smaller. By what factor? That's what K is, okay? So now let's think about this a minute. As this gets bigger, and this is constant, as this gets bigger, now what would make that get bigger? What would make the parentheses get bigger? Or be bigger? A big difference between the surrounding temperature and the coffee temperature. Let's say the coffee's boiling hot, 190 degrees. Okay? Is that boiling? That's not boiling. What's that, 212? Well, I don't know what the boiling point of coffee is, but anyway, it's probably pretty close to that. All right. So 190 degrees, hot coffee. 190 degrees, and the temperature in here is 70. So that's a pretty big difference. So that means that this is going to be fairly big. Now, what does this represent over here? T prime. Well, the rate what? The rate the coffee's cooling. The rate that it's changing, which would be decreasing, right? The temperature's decreasing. So the rate, so when the coffee's really, really hot, this is pretty big here, this difference. So this would be pretty big. It'd be cooling pretty fast is what we would say, right? But what if the coffee was 75 degrees and it was 70 in here? Pretty small difference. This would be pretty small, right? And that makes sense. If the coffee's about the same temperature as the room temperature, it's probably cooling fairly slow. So this kind of makes sense then, right? That this is probably a true scenario. So it's pretty, and that's a pretty easy equation. And it describes that situation pretty well. Starting out cooling pretty fast and then leveling off, right? Probably some sort of exponential kind of a situation. And it turns out it is. Okay, turn to the next page and read number 48. Read problem 48. Just read the problem. Don't read parts A, B, C, D, and E and all that. Just read the introduction there of number 48. Now, the first sentence is the important part. The rest of it tells you about Torricelli and then they actually give you the differential equation. So let's pretend we only read up to the parentheses. Let's pretend we only read the first sentence because that's what I might give to you next week. I might give you that first sentence and ask you to write the differential equation. So let's read through it. When the valve at the bottom of a tank is open, let's think about one of those blue coolers from the training room, right? And you got the spout down here, right? Okay? So we got liquid in there. Let's call that Y. Let's call Y the depth of the liquid. Okay? When the valve is open, the depth of the liquid drops at a rate proportional to the square root of the depth of the liquid. So, what would you write? The rate, Y prime, is proportional to the square root of the depth of the liquid. And the depth of the liquid was what? Very easy to write. Now, I know you're probably thinking I'm missing something here, right? Okay. Well, let's talk about that. So how would you have known to put a negative there? Who knows? You wouldn't have. You'd have just written this. You'd have been correct. If you wrote this, you'd have been correct. Now you say, hey, they have a negative there. Let's talk about why that negative's there and why it really doesn't matter if I put it there or not. Another question I might ask you, I might give you a situation like this, and I might say, is K positive or negative? Is K positive or negative? Well, no. Okay, I'm glad you said that. This drives my Algebra 1 kids nuts. When I tell them why we should not call this negative x, why should we not call that negative x? Because what if x is a negative 5? Then this is positive and this one's negative. And they go crazy. This is negative, this is positive, and that just drives them nuts, right? So K could be negative here, or it could be positive, right? Doesn't matter what sign we put on it, right? So what is it? What do you think? What's your gut reaction? Yep. Okay, you think negative because it's empty. So the liquid is dropping. Hey, this is a chart problem. Y is the depth, right? What's Y doing? Decreasing. But here's where you got to be careful, because that's pretty close, Spencer, but it wouldn't be good enough. If you say K is negative because Y is decreasing, that is not a valid rationale. The fact that Y is decreasing makes what negative? Y prime negative, not K. The fact that Y is decreasing. So here's how I would do it. I would do this. I would say, okay, this is negative, and I would give a reason. That's because Y is decreasing, right? So this is negative because Y is decreasing because the depth is dropping. Now what about this over here? Y is the depth. What do we know about the depth? That's positive, right? And when you do the square root of it, right? I mean, that's positive. So that's a positive value, has to be. So what's K got to be? Right? I mean, this is a depth, has to be positive. And so K has to be negative to make that equation work. All right? But here's why Spencer's rationale, though, wouldn't work. Because, so the way I've written it, K would be negative. But now if we go the way the book wrote it, the book put a negative on it. Right? Well, now what's K? In their version, what's K? K's got to be positive. Because then this negative on here will make this side be negative. See, so you couldn't say K's negative because in this problem, the depth is still decreasing. But K is positive, right? Okay, so the depth decreasing tells you that Y prime's negative. And in this case, K would be positive. So I might give you a differential equation like that. Explain the situation, maybe give you the differential equation, and then ask you, is K positive or negative? And you would rationalize it, and you would explain it based on what's happening in the problem. A little bit of chart stuff there, right? And that kind of thing. Yes?
If it was filling up, then you'd say Y prime is positive because Y is increasing.
That's exactly right. If you were filling up the tank, Y would be increasing, so Y prime would be positive. That's exactly right. Exactly right. Okay? All right. So there we go. That's about all there is that we're going to have to do on the quiz when it comes to differential equations. And we'll practice some more. The only thing we haven't done today that we did do in a problem yesterday was this one right here where we said solve the differential equation. And it was one of those types where all we have to do is an antiderivative. So we just did the antiderivative, just a simple antiderivative. And then we plugged in, then we had an initial condition also that time, so then we stuck that in and solved. Okay? So maybe if we don't do one of those on homework today, we'll talk about it Monday maybe. But other than that, that's pretty much the story on differential equations for right now. All right, so let's move to the local max min. So let's be a good chance to take a minute break and stand up and move around a little bit, and we'll talk about the next, those other couple sections. Yes. Shut the door. For how long? About 1 minute. Okay.
You can time us, Mr.
All right, ready, go.
He actually is.
All right, have a seat here. Let's do some top secret stuff. Let me give you a couple answers to the quiz that Cody won't know about. All right. Let's look at number 37 and 38 on page 137. 139, excuse me, 139. Now, this would be a perfect example of how much time?
They're coming back. They didn't have their microphones.
40 seconds? Okay, I got 20 seconds. All right. So this would be, I can't remember if I was telling this, you guys or the other class, but again, I use my algebra class as an example of how you learn something and you kind of understand, and you got it down cold, and then you learn something new, and then it screws you up on what you used to know. Okay? And here's a great example from my algebra class. This is what we've been doing here lately. You know, we were working on 2x plus 3x. Did I show you this the other day? I did? Yeah, 2x plus 3x, and they just got it cold, 5x. And then I show them how to multiply those two, and then they get this. And then all of a sudden I ask them to add those, and now they got 5x squared. Right? Now they want to add the powers, and they never did before, but now all of a sudden they do. Well, it's kind of the same thing here. We had all this stuff from chapter 1, the stuff we learned originally, and then we start bringing in some of the new stuff, and then it muddies the waters for some of that other stuff. And so we got to keep spiraling back to it. Here they ask you for average velocity. What's that mean? They gave you a function here too. It means slope between 2 points. And so this is the position, like in meters or whatever, and they want the average velocity. Well, that's just, and they gave you endpoints, 1 and E. So all that is the position at E minus the position at 1 over the time interval. So this is just how much distance it traveled divided by how much time it took. That's all you need. Average. It's not a derivative. Okay? So what this is doing is giving us some practice with our new functions we've been dealing with, but also some old ideas. So all we do is plug an E in for ln. What's ln E? 1. We plug a 1 in. What's ln 1? 0. Those are two values we need to know. ln of E is 1, and ln of 1 is 0. And so there it is. That is our answer for part A. Average rate of change is slope between 2 points. Now in part B, they wanted to know instantaneous. What's that mean? That is derivative. Yes, that's the prime. So and so this brings in our new stuff as far as our rules. What's the derivative of this function? 1 over t. Now you can kick out or you can tack on the 1 over ln e, the base, but that's just 1, so we don't need it. Okay, and now they wanted to know when x equals e. So you plug an e in there for t, and there's your instantaneous velocity. Finally, on 38, they wanted acceleration. What's acceleration? Position, velocity, double prime. So they want x double prime. Well, if we come up here to x prime, this is t to the negative 1. So we bring the negative 1 down in front, drop the power like so. So the derivative, the second derivative, would be negative 1 over t squared. And then they wanted that at what, 2? Is that what they said in 38? They wanted the acceleration at t equals 2. So we plug that in, and we get negative 1/4. Negative 1/4 is the acceleration. Okay, so that's old stuff, position, velocity, acceleration, but with a new twist because we've got this new function we just learned about its derivative. Okay, and so it's just kind of reviewing average rate of change, slope between 2 points, derivative, second derivative. All right, and we talked about the bank problem, so let's jump to page 147. And let's talk about 39 and 44. All right, was this 39? Okay, now we're getting into the territory of this stuff from the quiz. Max, min, okay, number lines, you know, and then the new thing we did yesterday, which was the global max, min, the list of candidates and all that stuff. So, these problems, any max, min problem always starts the same way, and that's by doing what? F prime, right, finding the derivative. So, we do the derivative. This would be a no calculator problem. And we set it equal to 0. And so we go to solve this. I saw a few people get this far, and then there was a lot of you had nothing much after this. Where does cosine equal negative 3/2? Oh God, can that be over here? Is there any place? Never does. Cosine has got to be between negative 1 and 1. Yeah, that's root 3 over 2. Yeah, you're thinking of root 3 over 2. Negative 3/2 is negative 1.5. Cosine can't ever equal that. It's got to equal something between 1 and negative 1. So this is, but now, we don't just stop. I mean, that just means there's no stationary points. There's no place where the derivative is 0. So what does that mean for our problem? There's no local max or min, right? That's where the stationary points happen. So one of the things they want us to do was local max and mins. This is where we would have done the number line, right? And put them on the number line, but we can't because there are no local max and mins. Or excuse me, there are no stationary points, so we don't do it. So there we go. We just say no local max mins. Okay? So now let's talk about global max mins. What did we say to do yesterday for global max mins? Group candidates, right? Well, there's no stationary points. Our candidates are stationary points and endpoints. There's no stationary points, and our endpoints are x equals 0 and x equals 2 pi, right? Because they told us that the interval here was 0 to 2 pi. So what do we do with our candidates? Yeah, we do a list of candidates, and we plug them back into the original function. If we were doing a number line, we'd plug them back into f prime. But here we plug our stationary point. Here we plug them back into the original function f. We do a list of candidates. So we come up here and we put 0 in and we get 0. We put 2 pi in. Let's see, the 2's that cancel. You get 3 pi. Sine of 2 pi. Let's see, sine of 2 pi is right there. Sine is the y value at 0. So there it is right there. So there's our max. So the biggest one's the max and the littlest one's the min. I would just give the y value. Now I know in this problem it said give both coordinates, so if you look it up in the back, they give it as coordinates. But normally we just want the max and min value. We just want the output. So the max is 3 pi and the min is 0. Now, this morning I shared this with the group, and I might as well tell everybody here. As you get more comfortable doing these problems, you might have noticed something right back here. This is, if you're going to graph this, let's go back to chapter 1. you're going to graph this. This is a cosine graph shifted up 1.5. Would that be this? This is f prime, though, right? This is f prime. So it doesn't have any zeros, does it? It never crosses the x-axis, right? That's what we were just talking about here. So if you graph this f prime and shift it up 1.5, you say, oh yeah, there's no stationary points. It never crosses the x-axis. What else? If this was chapter 1 and I gave you an f prime graph that looked like this, what else would you tell me? It's always, no, oh, well, f prime's always positive. This graph's always above the x-axis. If f prime's always positive, what's f? Always increasing. So now let's compare, now let's talk about global max min. If the graph's always increasing, where's the global max? At the right edge. And the global min is at the left edge, right? So you wouldn't have had to do a list of candidates. It's kind of like that T-chart. Remember I said Lilliman kind of came up with his own way of explaining that one, and for that problem it worked fine. But I like the T-chart because it kind of works all the time. Well, it's the same thing here. List of candidates will almost always work. Most of the time, 99% of the time. List of candidates is the way to go. But on this problem, you could have said, hey, because f prime looks like this, f is always increasing. Since f is always increasing, the max, the global max has to be at 2 pi, and the min has to be at 0. You could have done that as your rationale and it'd been just fine. But it doesn't always work that way. So a list of candidates tonight almost always works. Now, I said almost always. What would be a situation where a list of candidates wouldn't work? A list of candidates wouldn't work. Hint, list. Hint, candidates. There's only one candidate, a list of candidate wouldn't work. Now, well, how could you ever get only one candidate? Well, sometimes they give you a function and don't give you any endpoints. So then your only candidates are stationary points. So what if there's only one stationary point? Why couldn't you do a list of candidates with only one candidate? What's the point of doing the list? To compare, right? You want to compare which one's bigger, which one's smaller. If you only have one candidate, you can't really compare, right? So in that case, say you had an upside down parabola and no endpoints. There's no global minimum because it goes forever, and the global max would be up at the stationary point. So if there's only one candidate, it have to be not an endpoint, it have to be stationary points. Do a number line, and then you could say, hey, the graph's always going up, always going up. I'm not going to give you one of those. Later on, we'll get into some of those situations. We'll have to consider that. For right now, they'll be basic. You'll have endpoints. You know, there might not be any stationary points like this one. There'll be endpoints. You'll be able to do a list of candidates on any one that I give you right now. Because I want you to just be able to do these basic ones and go through this process. Okay? All right. Let's go to 44. And then we'll give you some. That should be, yeah, that should get us through here. And then we can, of course, this one takes a little while. But let's go through and then I'll give you some very much like this to work on. All right. F of x equals 2, what was it? Cosine x plus. All right. And as I explained to the people this morning, and I kind of apologize, I hope nobody spent too much time trying to figure this out as far as getting it. I think we talked about using your calculator. This one's got a 2x in it. Now, we can do this without a calculator. This one could be done no calculator. I'm not going to ask you to because we're not going to get that depth and that much in depth into the trig. To be able to solve this, we do the derivative, fine. But to be able to solve it with that 2x in there, you'd have to substitute out a double angle formula like we would find in Appendix F, and you'd have to then do some more algebra to it and so forth, so on. We're going to keep our trig ones fairly basic for right now. Okay, so you would not have to do that. All right, so we're going to get your calculators out here. Okay, so you got f prime, which we could do without the calculator. Matter of fact, I'm not so sure it wouldn't be faster without the calculator. but it doesn't hurt to maybe even just check it. So we can do the derivative. So you remember where that's at is next to the 9. We can go grab the derivative. We put the x down here. Sometimes it's nice to double check. You got 2 cosine x minus sine 2x, and there's the derivative. Now that looks, did I do that right? Oh, no, it wasn't minus. I did that. It's supposed to be a plus. There we go. Now that's probably not the order you would have done it back here. If you were doing it, you probably would have had negative 2 sine x. And then we got kick out of 2 cosine 2x, right? And then that's got to equal 0. Don't forget you got to set that equal to 0. If you're solving an equation, you've got to have the equation on your paper. So you've got to have that equal 0. Some of you on the quiz just did the derivative and nothing else. You've got to put on the equal 0. Okay, now what's the first question they ask us in 44? Stationary points, right? All right, so I got ahead of myself here a little bit. So I did the derivative, set equal to 0 to find my stationary point. So we can do this on the calculator now. So we go to our menu to solve. Now this is something I want you to be able to do for the next quiz, is to get on your calculator and solve a trig equation, all right, using that vertical bar thing that I showed you yesterday. So we go solve. I went up and pasted in my derivative right here. You could just type it in, hand type it in if you did it by hand. I got to put in the equal 0. I got to put in the comma x. And then I go to the outside of the parenthesis. So you've got to put in the equal 0. You've got to put the comma x all inside the parenthesis. Then this problem is limited from where to where? 0 to pi. So we go in here, control and the equal sign here, and that brings up, we get this vertical bar, which is not absolute value. It means with or such that. And we want to do it with the condition that x is between 0 and pi. So we go 0 less than or equal to x less than or equal to pi. And I would always, when I'm using my calculator, hit Control Enter probably, because I know the reason I'm using calculator probably doesn't come out nice. And I think even if you don't, it gives you a decimal on this one anyway. Now it turns out that that's pi 6 and 5 pi 6, to be honest with you. Those decimals are pi 6 and 5 pi 6. So if we would have used a double angle formula and worked that all out, we could have gotten that. All right, so those go on those are my stationary points. 0.524 and 2.61, what was it, 618. So those are my stationary points. So that answers part A. Okay? What's part B want to know? Where is F? Where is F decreasing? So what do I do for that? So how do I see where F prime is negative? Number line. If I want to see where F is decreasing, I want to see where F prime is negative. And so I do a number line. So I label this F prime. I put on 0.524, 2.618. Pick some numbers in between, 0.5, 2, 3, and I'm going to do what with those numbers? Put them into F prime. Now, I'm going to show you something. Show you something I don't think any of you know. Maybe you do, but I don't know. For those of you who've been bored and I haven't told you anything new today, and it's all been, you knew everything so far, I think maybe I got one new thing for you. We need to plug these in there. Probably we got our calculators, right? So the long way to do it would be to type in, here's your derivative right here. So to take 0.5 and put it in for those x's. So I can type that out. And then put in 2, and then put in 3. Okay, and that'd work fine. And if you're most comfortable doing that, then do that. A shorter way would be to just, since I already have the derivative up here, I'll grab it. If you don't have it, you may have to type it. But here was my derivative. Here was my f prime. I can use the vertical bar again, because the vertical bar means width. And so what I'm telling the calculator here is I want to do this with x equals 0.5. Now the nice thing about doing this is when I hit enter, I can now arrow up and grab this again and just change the 0.5 to a 2. And then I can go up and grab it and change the 0.5 to a 3. I have to type that in every time. So it's a little bit shorter. And then some smart aleck in the other class thought that was even too much work and wanted to know if there's even more of a shortcut. Could we plug all 3 in at one time? So we did a little searching, and sure enough, we can. If I grab this, so I got my derivative, vertical bar, x equals, and if you see the right parenthesis in blue is a curly bracket, that is used for lists. I can actually type in 0.5, comma, 2, comma, 3, and it'll plug all 3 of those in and return me those 3 values, all plugged in. And so I get a list. Oh, and I need to hit Control Enter. And I get a positive, then I get a negative, and then you can barely see it at the edge there, I get a positive. So you can do any one of those, it doesn't matter. I mean, if that makes you comfortable, do one at a time. If you'd rather just literally plug them in for the x, you feel better about that, do that. Doesn't matter. Okay? So we get a positive, then a negative, then a positive. All right. Positive, negative, positive. So there we go. There's the answer to when it's decreasing from 0.524 to 2.618. Or was it decreasing or increasing? Decreasing, okay. So between 0.524 and 2.618, it's decreasing. All right. What about the next question? Find the max and min values of f. That's global. If it doesn't say, when it's worded that way, that's global max min. Local max min, they'll say local. Or another term they sometimes use is relative. We won't get into that till later. I'll always say local for right now. It says find the max min value. They mean global. So we need a list of candidates. So we're going to plug those into the original. So we're going to plug in 0. We're going to plug in 0.524. We're going to plug in 2.618. We're going to plug in pi. Now I'll let you finish that. But and we could do the same thing with that vertical bar, right? We could type in our original function f on our calculator, do the vertical bar, plug in 0, plug in that, plug in that, plug in that. Now one thing I might caution you on, it's not probably a big deal right now, but it could become later, and we'll make more of a big deal about it later because as we get better at this stuff. If you want your final answer to be accurate in 3 decimal places, you probably should plug more than 3 decimal places in when you plug in the 0.524. You might want to plug in 5 or 6 decimal places, but for right now, I'm probably not going to. I'm probably not going to cost you much, if anything, right now. But that's something to keep track of. You know that from science. If you have a calculated value and then you use it in subsequent values, it may make your final answer not accurate enough. Okay. All right. So there's your list of candidates. All right. What was the last thing then that it asked? Where is F concave up? Where do we look for concave up? But how do we can't tell when f prime is increasing? When f double prime is positive. How do we tell when f double prime is positive? Same way we told if f prime was positive. We do a number line. Now this is the one I've been holding off on you. I told you didn't have to do the inflection point part of that other problem. Okay, well let's add it in right now because it's really no different than what we've been doing. I didn't want to muddy the waters anymore until we had done a few more examples, but now we can do it because it's really the same thing. How do you tell? Look what we've been doing. We've been talking about chart stuff, increasing, decreasing, local max min. That's when f prime is positive or negative or 0. So we do a number line. Well now, if we do a number line on f double prime, that'll tell us concave up, concave down, or possible inflection point. Okay? So, let's do that. So we need f double prime. Okay? Well, what's the derivative of negative 2 sine x? Why are we doing f double prime? Because they're asking us where is it concave up. So we want to know when f double prime is positive. So the derivative of this is negative 2 cosine x minus 4, because we're going to have to kick out another 2, sine 2x. So derivative cosine is negative sine, so we'll get a negative, kick out a 2, that'll be a 4. Then we want to set that equal to 0. We're going to set that equal to 0 because those are the numbers we'll put on our number line, and then we'll check on each side to see if it's positive or negative. All right, back to the calculator. Tell you what, let me just tell you what it is so I leave you enough time to get started on some homework. I'll just tell you, you do the same thing then. You go to your solve, you put it in, you do your solve from 0 to pi, okay, and you do your calculator stuff, so it'll be good to practice it. But you get 1.571. Does that look familiar? 1.57? It's pi half. Pi half. But anyway, doesn't matter. It's just, that's what it is. So, you would do a number line. You would label it f double prime. You put 1.571 on it. So you plug in a 1, plug in a 2. I'll tell you that when you plug those in, and you should try it, you should practice it using the calculator, you're going to have to do it, comes out negative positive. Now what does that number line tell you? Concave down, concave up. It also tells you then 1.57 is what? The inflection point, right? When we set it equal to 0, the chart tells us second derivative equals 0 is a possible inflection point. When we put it on the number line, we see this change. That tells us that f double prime or f goes concave down to concave up, so that is an inflection point. But what they asked was where's the concave up? So from 1.571 to pi. Okay? All right. So chart kind of stuff. Global max min is list of candidates. Trig. Now, the one thing we didn't get to practice much today was like unit circle stuff. So I'm going to give you one where you have to do some unit circle stuff again. Because on 39, it just came out there were no stationary points. We couldn't solve it at all. All right, so here's what our homework's going to look like. All right, and those of you online watching this, the assignment will be on the website. Thanks for listening.